For this lesson, we're going to be taking a look at something known as the ambiguous case of the sine law. And so this lesson actually builds off of two previous lessons. One of those is just the review of the sine law, and the second one was our discussion of obtuse angles. And in that discussion of obtuse angles, we introduced the idea of defining trigonometric relations and ratios in terms of a point with coordinates x and y, and in terms of the distance from the origin to that point, which we've labeled as r. And from there, we ended up with these new definitions of sine, cosine, and tangent in terms of x, y, and r. In that exploration, what we found out was that the sine of theta is equal to the sine of 180 minus theta. So the sine of an angle theta is equal to the sine of the supplementary angle to theta, because supplementary angles add up to 180. We also found out that the cosine has a similar relationship, except for in the case of cosine, there's a negative multiplier between the two. So we need to focus on sine. Because these two things are equal to each other, we call that ambiguous. We don't know which one we're talking about. Are we talking about the acute angle? Or are we talking about the obtuse angle? We have two angles that give the exact same value for sine, which means technically we could have two different triangles that seem to have the same answer when dealing with sine. And since this note is focusing on sine law, if sine itself is ambiguous, then that means there's the potential for the sine law to be ambiguous. So how do we resolve this? So just a reminder of where did that come from? Why is sine ambiguous? In quadrant 1 and quadrant 2, the y coordinate is positive. That's what it means to be in quadrant 1 or quadrant 2. Anywhere up here, you have a positive y coordinate. So the y coordinate here is always positive. The r value, which is the distance from the origin to the point, well, that's a distance. So a distance is always positive. So this is positive over positive, which means so long as the y value has some sort of symmetry, or sorry, so long as the point has some sort of symmetry across the y-axis, then you're going to end up with, whether you're talking about this angle or whether you're talking about this angle, you're going to end up with the same value. So for example, if you were to plug this in your calculator, sine of 30 degrees, you'd get 0.5. Sine of 150 degrees, you also get 0.5. Now that's clear enough, that's fine. That's two separate expressions that I just evaluated there. But what about going in reverse? If I start with sine theta equals 0.5, from what we just talked about, there are actually two possible answers here, 30 and 150 degrees. So how do I choose which one of those is correct? Can I choose which one of those is correct? And the other part that we're going to make use of here is the sine law. There are two cases for the sine law. We use it when we are dealing with some sort of non-right triangle. And in particular, the sine law is useful when we have two angles and the enclosed side. So angle, side, angle. Or when we have two sides and the non-enclosed angle. Side, side, angle. If I start going around the triangle, side to angle. So in that case, I would use the sine law. Now, the thing is, this one is trying to find a second side, whereas this one is trying to find a second angle. And this one is the one that we're going to be looking at today, because it's when you find a second angle that you're going to end up using an equation like this, and you're not going to know, is that second angle, in this case, for example, let's say we did the sine law and we ended up with sine theta equals 0.5. Is my answer actually 30 degrees or is it 150 degrees? Now, whenever we solve for an angle using the sine law, we have to consider these two possible solutions. And these solutions will be an acute angle or an obtuse angle. There's a very special situation where that won't be the case, where you might get a right angle. If you identify that earlier, you should just be using right angle trigonometry, not the sine law. But sometimes I could imagine a situation where the sine law seems like the right thing to use, so you go ahead and use it. But in general, you're going to get two answers, one acute and one obtuse. Depending on the amount of information that's been given in the question, you might be able to piece together, just using common sense, which is the most appropriate. For example, if one of your answers violates the angle sum theorem, that all the interior angles add up to 180, you can discard that and you just list that as my answer. We've talked about the fact that longer sides correspond to larger angles. So that means the side across from an angle, you're going to have a long side across from a large angle, you're going to have a small side across from a small angle. And just the general geometry of a situation might even give you some clues. If you have side-side angle and you're using sine law, there are three general situations that you could encounter. No solution, so it's actually possible that you can't make a triangle. One solution, so there's only one possible answer. And then two solutions, this is where we get into the ambiguous case. You could argue that all of this leads itself to some ambiguity, but that's not actually true. It's really just this case number C that is the ambiguous case. The idea of no solution or one solution, that's just a consequence of the numbers in the question and the configuration of the situation. So let's start off with an example. Albert and Bell are conveniently named A and B. They're launching a weather balloon into a cloud. Albert's rope is 20 meters long and it makes an angle of 50 degrees with the ground. Bell's rope is 16 meters. How far is Albert from Bell? And it says to include a sketch, which is what I would do anyway, but I really want students to be doing this. So here's the ground. I'll do that in green. I will put Albert here. And Albert's rope, which we're going to assume the rope is pulled taut or tight. So Albert's rope makes an angle of 50 degrees with the ground. We know that. Attached to Albert's rope is a weather balloon. So I'm going to call that, let's say, W. And then we have Bell. Now Bell's rope is 16 meters, so Albert's rope is 20 meters. And so if what I've drawn here is roughly 20 meters, my other line that I have to draw down to Bell has to be shorter than that. So I'll do something, how about that, 16 meters. It doesn't tell us what angle Bell makes with the ground, so I have to leave that blank. There's B. And the question wants to know how far is Albert from Bell. So in other words, it wants to know what is the distance AB. Okay, so we take a look at this. I have side-side angle. So I have side-side angle, which means I'm going to use the sine law. I've got my three vertices labeled, which means I can also label my sides. This would be side A. This would be side B. This would be side W. Let's make the distinction between lowercase w and capital W a little clearer. Okay, so now using sine law, you can probably see what version of the sine law you need to use here, but I'm going to go ahead and write it out. First of all, I'm interested in a side here. The side I'm interested in is actually the side W. So I'm going to write W over the sine of the angle W is equal to, let's see, A, which is 16, over the sine of the angle there, which is 50 degrees, is equal to, I have 20 meters over, but I don't know the angle at B, so I just have to write the sine of B. So to solve this, this is what I have to start. Now take a look at what we've got here. First of all, W and sine W. I don't have anything for this ratio, so I can't make use of this first ratio at all. On the other hand, I have both parts of the second ratio. That's good. I can use both of them. And over here, I don't have sine B. I'm not even really interested in this, but unfortunately, in order for me to be able to work over here, I'm going to need to solve some other things first. So it looks like this is the portion of the sine law that I'm going to have to make use of. So that means I'm actually solving for the angle sine B. So I'm going to rearrange this as sine B over 20 over the side B must be equal to sine 50 degrees over 16. And then I can rearrange this. Sine of B is equal to 20 sine 50 degrees divided by 16. And I end up with B is approximately equal to, so first I'm going to calculate this, so 20 sine 50 divided by 16, and then I'm going to take the inverse sine of that answer, and I end up with approximately 73.2469 degrees. Now, obviously I've already talked about this in quite a bit of detail, which is the fact that sine has some ambiguity. But if we take a look at the diagram that I've drawn here, so actually, you know what, let's go ahead and fill this in. Or B is approximately equal to 180 minus 73.2469 degrees. Let's leave it at that for now. Now, based on my diagram, it very much looks like this is the correct answer, 73.2469. It looks like I've got an acute angle here. So let's, for the sake of argument, we're going to use the acute value of B. So if I use the acute value of B, then I can now find the value of the angle W. The angle W is just equal to 180 degrees minus 50 degrees minus B. And so that means W is equal to 180 minus 50 minus my acute answer. So W works out to be 56.7531 degrees. And now that I have W, so I have now found the angle W, which means I can now find the length W, which is what I was interested in the first place. So now I get the length W over the sine of W is equal to 16 over the sine of 50. So notice now I'm using a different pairing from the sine law. I'm using this one in green. And W, the length W, is equal to 16 sine of the angle W over the sine of 50 degrees. And since I kept my answer from before in my calculator, I can go straight to my answer here. And so I have to take the sine of my answer, and I have to multiply that by 16, and I have to divide that by the sine of 50 degrees. And I end up with approximately 17.5. So therefore, Albert and Bell are 17.5 meters apart. And you might say, okay, this is done because I did take a look at my diagram. I used common sense to tell me that this angle looked like an acute angle. It's not greater than 90 degrees. But is that the only possible configuration? And the answer is actually no. We could have also done this question a very different way. Well, not very different, but different. Here's the ground. Once again, I'm going to start with Albert. I'm going to start with a 50-degree angle, 20 meters of rope or of string. I've got my weather balloon here. And now, and it helps because I've got a little bit of foreknowledge here, I could draw Bell right there. Now I'm going to have to tune my diagram a little bit because things are going to get quite crowded. So I'll put this 50 degrees a little bit smaller in that corner. This is still a valid, and Bell's string is 16 meters still. So now you might look and say, well, hold on, that angle, there's that acute angle again that we had in the previous diagram, but that is outside of the triangle. What is the angle inside the triangle? It is obtuse. And so for this obtuse angle, we actually end up keeping, if we go back, we ended up with sine B equals 20 sine 50 over 16. Sine B equals 20 sine 16 degrees over, no, I did that wrong. It's not sine 16 degrees. It must be sine 50 degrees. And so in this case, we're going to get B is approximately equal to, so I'm just going to re-verify my calculation. Take the inverse sine of that. But now I'm going to do 180 minus that answer, and so I end up with 106.7531. Now, you wouldn't normally write it this way as if they're two separate solutions. You would actually say case 1, acute angle, case 2, obtuse angle, and then you would redraw your diagram. I'm just trying to illustrate to you to start here that depending on how you visualize this question, one or the other of these might be the thing that makes a lot of sense to you. And so now from here, I followed the exact same steps that I did before, which is that I have the angle B, which means that the angle W is equal to 180 degrees minus 50 degrees minus the angle B. So the angle W is approximately equal to 180 minus 50 minus that answer. And that's still a valid angle, 23.2469 degrees. And now I can use the sine law again, which says that the side length W divided by the sine of the angle W is the same as the side length, and again using what we had before, the side length for A divided by the sine of the angle for A. Notice that I'm actually using, it's the exact same relation that I used before. It's just that now this angle W has changed. And so I end up with W is equal to 16 sine of the angle W divided by sine of the angle 50 degrees. And I end up with W is approximately equal to, it's going to be 16 sine of my previous answer divided by the sine of 50 degrees. And I end up with W is approximately equal to 8 point, and this is my final answer, so 8.2. Therefore, Albert and Bell are 8.2 meters apart. And that varies quite a bit from what I got here, 17.5 meters apart. So hopefully that convinces you that this idea of ambiguous case and two answers, this is not just an abstract thing. You can have a very somewhat realistic situation. It's not so hard to imagine two people flying a balloon, And under those conditions, then you can have two answers. So how do we explain that? I've got some pre-made diagrams here that I'm just going to go through. In class, I'm going to go through this in a more dynamic way. Unfortunately, in these video lessons, it's not an easy thing to do. So I've got these pre-made diagrams instead. So in this case, we have what happens if, first of all, Albert, in this case, notice I'm still using Albert here, A. I'm using the same angle 50. I'm using the same length 20. So I'm starting off with a lot of the same stuff. I've drawn this. I think it's most convenient to visualize this. You can see I've drawn the ground here, and there's no end to it. The ground just extends horizontally. Now, in our question, the length of the other string was 16. But what if, for example, in this case, what if I tried to use 10? I used geometry software to do this. I used GeoGebra to do this. And you can see with this configuration of this angle and this length, 10 is actually not even enough to reach the ground. So if this was Albert and Bell, Bell would be here hanging in the air. And of course, that's not realistic. That's not even possible. And most importantly, from a geometry point of view, that doesn't make a triangle. Now, what is the determining factor here? In order to reach the ground, what is the shortest distance to get to the ground? And the answer to that is wherever that line meets the ground at a right angle. So if we look at this as a right angle trigonometry problem, B becomes my hypotenuse. This angle, with respect to this angle, what is this side? That would be the opposite. So that's the one we're interested in. And so what we end up with is the sine of the angle 50 degrees must be equal to, let's make that 50 a little bit better. The sine of 50 degrees must be equal to the opposite divided by the hypotenuse, which is 20, which means the opposite side must be equal to 20 sine 50 degrees. And that means the opposite side in this case is approximately equal to 15.3. So 15.3 is this distance from here to here. So if the length of the string, or the length of this side, is less than 15.3, you can't touch the ground, and therefore you can't have a triangle. And if you can't have a triangle, you have no solution, which I really should have said here, no triangle, which means no solution. So that's our first case. So you can see this is how we get no solution. Physically, this is not possible. But what this is saying is that if you're just given a set of numbers related to a triangle, not all of those numbers actually make a triangle. So this is one of those cases. Okay, the second case I talked about was one solution. There is an easier and a more difficult version of one solution. So that's what I'm calling here case 2A. In the case of one solution that's the easiest, the length of side A is the exact right length to make a right angle. So it just touches the horizontal here. And so we end up with a right angle triangle. We already calculated the length of A required for that. This is always going to be your starting point. If you are asked to do a question to answer something about the ambiguous case, this is not like our Albert and Bell question. Our Albert and Bell question, if you're asked a question like that, you draw your diagram, you do your math, you get to an answer, and if you're using sine, you end up with the ambiguous case, you end up with two answers. You then split off your answers and you pursue each one of those individually. But there's another type of question where you can be asked, under what conditions will I get no solution, one solution, two solutions? And this is just like when you were looking at a quadratic formula and wondering about no solution, one solution, two solutions. one solution is the place where you want to start because one solution has a single answer. And in this case, it is the easiest one to do the math because it is just right angle trigonometry. You find this answer, and then anything smaller than this answer means no solution. A little bit more complicated though is, okay, well that means larger than this must mean two solutions, right? Yes, but not always. So a little bit larger. So for example, 15.3 was our cutoff there. So what about 16? Well, this is now the Albert and Bell diagram exactly. Here's the angle of 50 degrees at Albert, 20 meters of string for Albert, 16 meters of string for Bell. The first way I drew it would be this triangle with an angle here of 73.2. The second possible way, you can see we've got this outside line as the first possible location for 16 meters of string. This dotted red line is another possible location for 16 meters of string. And that would result in this triangle, which actually has an angle of 106.8 degrees. So once we've got that taken care of, those are our two solutions. But what if the string keeps getting longer? If this outer string keeps getting longer, the triangle just keeps getting bigger and bigger and bigger. But if this inner line keeps getting longer, then we're going to get closer and closer and closer. Eventually, we're going to end up right next to Albert. And the moment that we are on the same location as Albert, do we have a triangle anymore? And the answer to that is no. What if we go past Albert? If we go past Albert, we have a different triangle because this angle has to be in the triangle. And if we go past Albert, this angle's not in the triangle anymore. So once again, no solution there. So how does that resolve itself? If it gets too long, then we just have this one solution. And when does that occur? Going back here, if we went 16 and then to 17, we'd get closer. 18, closer still. 19, even closer. But if we got to 20, the only way to have that on this left diagram would be if Albert and Bell were standing at the same location. 20 is no problem over here. It just means that B is further out to the right. So that's our threshold. Our threshold to go back to one solution is if this side is greater than or equal to the side that's next to the angle. Remember, all of this stuff is based on side angle for the sine law. Side angle. So if the first side, if the side that's not next to the angle, that would be this one, if it's greater than or equal to the second side, so this would be A and this one would be B. And then this would be the angle A. That's the arrangement we've got here. If A is greater than or equal to B, then we have one solution again. Now, what I've shown you so far is for an acute angle. There's actually fewer cases. What if we said that Albert, well, it doesn't really work well with the balloon, but let's just imagine another situation where this point A has an obtuse angle. So in this case, I've done 125 degrees. First of all, we start off with that same limitation as before. So let's extend the ground. And you can see this point does not even reach the ground or the horizontal. What would it need to be to reach the horizontal? Well, for it to reach the horizontal, we're going to have to... Oh, I'm sorry. That's not correct. The horizontal matters there, but even if we reach the horizontal, it's still not a triangle because it has to contain this angle. So let's say we extend this down and it reaches the horizontal. Okay. Does that make us our triangle that contains 125? No. So let's say we make it longer and we bring it to here. Does that contain 125? No. Make it longer still. Does that contain 125? No. Make it equal to 20. Does that contain 125? No, that's just a straight line. So it's not until we go past A that we get a triangle. And so that's why I say if the side A, for example here 14, if it's less than or equal to B, which is 14 is less than 20, no triangle. Made quite a mess there. Let me just clean that up. So make sure you remember, even there I had a momentary lapse. You have to include this angle in your triangle that you're making. And so as I showed you there, the only other option is if this side gets long enough, if it's greater than side B, so this is side A, if A is greater than B, then it extends far enough to go past A, and then you end up with a triangle. So this one's easier in the sense that there are fewer cases to consider, but I actually think that this one's much more difficult to visualize. Okay, so that's it for the ambiguous case of sine law. And I say that's it as if, oh, we wrap that up and that's easy. It is not easy. You have to spend some time thinking about it, but it does make sense if you just break it down. One thing I really want to encourage you to do is whenever possible, try to put it in terms of the ground or the horizontal and build things with respect to that. If you start to move these angles up into other positions, even I find that quite disorienting, and I find positioning things as if something is on the ground really helps me with my visualization.